So it's a pleasure today to introduce Youngseog Chung, and he is a PhD student in the machine learning department here at CMU and advised by Jeff Schneider. He's working on a project in the autonomous decision-making thrust here at AI-SDM. And his research interests are in uncertainty quantification, calibration, and decision-making under uncertainty, which I believe is all parts of his talk today. So without any further delay, Youngseog, please.
Cool, thanks, Norm. All right, everyone, thanks for coming. As Norm just mentioned, I'm Youngseog, and I am a PhD student in the department, machine learning department, advised by Jeff. And today I'll be talking a lot about topics that I've been focusing on during my PhD so far, which is namely uncertainty quantification, specifically for probabilistic regression, so regression setting. Okay, so I'd first like to acknowledge my collaborators. Ian Char, who was a PhD student here, he graduated recently. Willie Naiswinger, who was also a PhD student here, he's now a professor at USC, and my advisor, Jeff Schneider. Okay, so I will first go into a bit of a primer about predictive uncertainty quantification, or UQ for short, and then talk about metrics or methods to assess it, namely calibration, and then go into the methods of some of the work that I've been working on, calibration for univariate probabilistic regression, and then extending it to multivariate regression. Okay, so just to set the stage, ML models are ubiquitous nowadays. They're used in a wide range of applications, and they range from your daily interactions with chatbots online, getting recommendations about what to see next, as well as in the physical sciences, in predicting protein structures and also plasma dynamics during nuclear fusion reactions. But one question that I think most of us might be wondering when interacting with these machine learning models is, can we trust these models, and should we trust the outputs of these machine learning models? And that's where uncertainty quantification sort of plays a role. It literally just means quantifying the uncertainty and making a prediction. And it turns out that reasoning about uncertainty can actually provide a lot of utility in terms of guiding your decisions. So you might have selective classification, for example, where you only make a prediction about a class when you're absolutely certain, and when you're uncertain, you can refrain from making a decision and have a human, for example, label it. In Bayesian optimization, reasoning about uncertainty will help you more efficiently query the points in order to find the maximum of a function. And in model-based reinforcement learning, it's been proven that reasoning about uncertainty in your dynamics model is necessary for the policy that's learning on that model to perform well when it's deployed in the real dynamics. And as it turns out, most of the machine learning models that are trained, that are deployed, that we use every day actually have a built-in inherent means of quantifying uncertainty, and that's with distributional predictions. So in the case of classification, scores that come out of, for example, a network will be turned into a categorical distribution through its softmax distribution. And if you have, for example, you have a drone for which you're trying to predict the next state, maybe given its actuators, you might predict the mean and log variance, which will then get translated into a normal distribution over the possible next states. And using these predictive distributions, you can quantify how uncertain or confident you are about the predictions. The left side for the categorical and the continuous, both being more uncertain states, and the right halves being more certain predictions when you're dealing with these probability distributions. So given that we're going to be quantifying uncertainty with these predictive distributions, how should we assess whether these uncertainties or distributional predictions are actually good? And that's where calibration comes in. So calibration is a notion of how well you quantify your uncertainty. And at a very high level, what you're trying to measure is how aligned your predicted probabilities are to the empirical frequencies of the events that you're predicting. So suppose we have this problem where we're trying to classify whether these images are a dog or not, and I find them pretty confusing. But suppose you have a model in the first column that outputs these probabilities for the class dog versus not dog. And based on those predicted probabilities, you will make a class prediction, which is on the second column. And based on your predicted class and the label, you will have a notion of correctness of your predictions or not. And what calibration tries to do is it tries to first ascertain a certain value of the probability you're predicting. And it tries to see if it matches up with the empirical frequency. So suppose we're trying to see if the prediction 2/3 or 66% is calibrated. Then you will collect all the instances for which you predicted 2/3. Then look at how often you were correct when you predicted 2/3. And in this specific case, you were correct 2 out of the 3 times that you predicted 66%. So you can be said to be calibrated for the probability of 2/3. And ideally, you want to be calibrated for every single probability between 0 and 1, not just 66%. Yeah, so to recap, you're trying to look at the alignment between predictive distributions for probabilities and empirical frequencies. And the procedure is to predict the probability for a certain value, collect all instances of when you predicted that value, and then look at the actual events or the labels. Does the event actually materialize that proportion of times according to the value that you predicted? So we just saw how the event is defined in classification. So in classification, you're looking at correctness. Is your predicted class correct? And does that align with the probability you attributed to that prediction? And in regression, which will be the focus of the rest of this talk, the event is the true value, so a continuous true value y being within the region of integration that you're defining this probability over. And we will go into more detail about what that actually means. Yeah, so we'll jump right into calibration for univariate probabilistic regression. So just to set the settings and preliminaries, to just be formal, we're looking at features that can be high dimensional in dimension d. But our targets will always be univariate. Later on, they'll become, that'll be relaxed and it can become multivariate. And given that we're predicting distributions over the targets, our ideal prediction is actually the true conditional distribution. So given any x, we want to predict the f of y given x. And small f here notes the PDF and large f denotes the CDF. And for the first part of this talk, we'll be heavily leveraging quantile functions. So just to give you a reminder of what those were. Quantile functions are just inverse CDFs. So if a conditional CDF takes in a value in the target space y and outputs the probability of observing a value below that value, the conditional quantile function takes in a value p, a probability value p, and outputs the value in the target space below which there's p probability. So in other words, p proportion of the density lies below the p quantile. Okay, so this is just a toy example of how calibration is measured in regression. So suppose you had 3 inputs, x1, x2, x3, and then for each of those inputs, you predicted these continuous distributions f hat given of y given x1, x2, and x3. And suppose you're trying to measure the calibration of the 2/3 probability. So in order to do that, you will first find the quantile that corresponds to the p equals 2/3 for 66%. And that literally means below that value, your predicted distribution has 2/3 probability. And suppose the true value y, so y1, y2, and y3, fell at the red stars. And you can see that in the prediction interval that's defined by basically -infinity up until the quantile, which is where you place 66% probability. the true value fell in that prediction region. And for the first data point, the second data point, it didn't fall in the third data point. So Y fell in my 66% interval, prediction interval, 66% of the time, or 2/3 of the time. So you can say in this case, the 66% quantiles are calibrated. And again, you want to be calibrated for every single probability, not just 66%, but every single value P between 0 and 1.
Can you hear me?
Yeah.
Yeah, very sorry to interrupt. You're not sharing the screen to Zoom audiences. Just a reminder.
It's not sharing.
I don't know. I don't want to.
That's okay. Okay, can you see it now?
Yes, thank you so much.
Yep.
Thanks, Yusha. Thanks, Norm. Okay, just to give, I guess, another visualization that makes it more seem like a regression setting. Suppose you have ground truth data points that are in yellow, orange, and then you're outputting these predicted distributions, which are Gaussian distributions. And we're visualizing them in the blue dots and shades, where the dots represent the mean, and then you're looking at bands that are plus minus 2 sigma. Based on each of these conditional distributions, you can draw the quantile functions, the conditional quantiles, which are in the dotted lines. And again, you're asking the same question. What proportion of the true observations fall below each of these quantiles? And you want the proportion of these observations falling below the quantiles to equal the quantile level. So suppose this is the 10% quantile, then you want these orange points to fall below these dotted lines 10% of the time. So you want 10% of the orange dots to fall below it. And for like 30%, you want 30% of them to fall below. Same thing for 50, et cetera, to 90. And for each of those pairs, for example, 10%, then you will map it to the observed data points on the y-axis on the square diagram on the right, which we call the reliability diagram. And you're calibrated if this plot lies in the 45-degree line. And in this case, it's obviously miscalibrated. And in a mathematical sort of formulation, that equation, we can define it as the equation on the left, sorry. It looks a bit hairy, but suppose you fix x, then you draw the peak conditional quantile. And you're looking at how many data points fall below the conditional quantile according to the true observations. Now you're averaging it across all of basically the whole domain. And the same equation can be expressed in this way. So both expressions are sort of readily used. Okay, so we've established that quantiles are quite useful, at least for assessing calibration and regression. And to produce or learn conditional quantiles from data, the pinball loss is really the standard de facto primary method out there. Yeah, so the pinball loss is stated as is on the slide. So given a target, which are target observations, a desired quantile level P, and a quantile prediction Q hat, the pinball loss is basically a tilted hinge loss. But if you optimize this, in the limit of data, you should recover the true conditional quantiles. And this is the established method in quantile regression, but it turns out that it can actually display pathologies when optimized with high capacity models, for example, neural networks. And this is sort of where some of my initial work in concerted quantification sort of dug into. And we can show that if you have a finite data set and you consider a calibrated, you can ignore the word average, but consider a calibrated solution. So you have conditional quantiles that are calibrated. Then it turns out there will always be another solution, another set of conditional quantiles that is miscalibrated. So it's less calibrated, has higher calibration error than the first solution, but it actually attains a lower pinball loss. So what this tells you is that the pinball loss turns out to be inadequate both for evaluation and for training conditional quantiles. And that's basically the gist of this proposition. And here's a visual that sort of demonstrates that phenomenon. You can ignore the red curve, so you can just look at the blue curve for now. And we're training a quantile model, a model that outputs conditional quantiles on a data set. And on the left-hand side, we're plotting the pinball loss on a held out set on the test set, basically. And you can see that it continuously decreases. The pinball loss continuously decreases until about epoch maybe 350, at which it attains the minimum pinball loss. And we're marking that with a vertical dashed blue line. And if we measure the calibration error along each of the quantiles that we're seeing during training, it turns out it attains the minimum at a point that's much earlier than the minimizer of the pinball loss. And at the minimizer, it has a very high calibration error. So to circumvent this, in some of my prior work, I proposed 4 different methods, alternative methods to train for conditional quantiles. In this talk, I will just go over 2 of them. The calibration loss, which is a method of directly optimizing for calibration when learning conditional quantiles. And the 4th one is group batching, which I'll get into later. Yeah, so the first idea is don't optimize for the pinball loss, but instead optimize for calibration directly. And the idea here hinges on the fact that when you're measuring calibration, you're averaging across the input distribution, fx or px. And in the infrastructure of training deep models nowadays, you always take mini batches, but these mini batches are actually samples from px. So you can actually get an approximation of what your calibration currently is based on the mini batch that comes from px. And if you're miscalibrated, you can basically tweak your quantiles such that in a manner that makes it more calibrated. The loss function, there are many steps, but essentially you're just optimizing this loss function directly. And this loss function, yeah, look, it's a bit long, but we can dissect it. So we have two cases. In the first case, your observed proportions were below the desired proportions P. And in the second case, it was opposite. So you will only look at what are the other, this term or this term. Suppose it was the first term where your observed proportions were less than P. So you wanted P proportion of the data points to fall below your P quantile, but you observed less. It means your quantiles were just too low. So you want to pull them up. And then what you can do in order to induce that property is you can take a loss with respect to the data points above these conditional quantiles. So if Y was above your conditional quantile, for those data points, you minimize the distance. And this will always be positive because Y is above Q hat. And same thing for the other case. If you covered way too many data points than you desired, so your quantiles were way too high, you want to push them down, then you can take the loss with respect to the data points that were below your conditional quantiles. And you can see that because these non-zero terms are defined for the cases where you have miscalibration, they're conditioned on being miscalibrated. You can see intuitively that it doesn't suffer from the same pathologies as the pinball light. That is, a perfectly calibrated solution is an optimum of the calibration objective or the calibration loss. And just to show you what that, what the idea there is, and how that sort of, how the loss acts to tweak your conditional quantiles, here's a visual where suppose you had a data set of 10 different data points and you were trying to estimate the 70% conditional quantile. And suppose this blue line was the true conditional quantile. And suppose you started with an initial prediction that was just a flat line. What the loss asks you to do is it asks you to first measure your calibration. You want 70% below the quantile, but you only see four points, 4 out of 10. So your coverage is 40%, your quantiles are too low. So what you're gonna do is you're gonna take a loss with respect to the data points that's above it. So after one gradient step, maybe it'll be pulled up a little. And that's your second prediction. You measure calibration again. It's still too low, you're only covering 50%. So you take another loss with respect to the points that are still above it to pull the quantiles a little higher. And eventually, hopefully you reach the desired coverage proportions. Okay, so that was the first idea. And then the second idea is something called group batching. So recall that when we measure calibration, we were integrating across the distribution of the inputs, Px or Fx. And when we take mini batches during gradient descent optimization, each of these mini batches are IID batches from Px. But it turns out that a solution of the notion of calibration that we saw earlier, one trivial solution of that is just the marginal quantiles of the marginal distribution Py. So suppose you saw horizontal lines just across the y space. And so basically it's a constant function with respect to x. But if they're marginal quantiles of y, then they're actually also calibrated. And obviously you don't want that because they're hardly going to be useful. So the idea in group batching is don't take IID batches from Px, instead deliberately batch according to the input features so that you can optimize for the calibration of each basically subdomain or locality individually. And you can see that as in the limit, if you reduce these subgroups smaller and smaller, in the limit, you will be optimizing towards conditional calibration. So it'll be optimizing for the calibration given a single data point connects. But obviously you can't do that in practice because you only observe one data point per X. So this is just a heuristic to sort of induce that property of more conditional rather than marginal calibration. Okay, so these are two ideas, and there were more in my previous work, but just to give you a sense of how these perform, you can just look at the red dot, which corresponds to Cali, standing for calibration loss, and this is paired with group batching. And on each of these plots, what we're trying to do is we're modeling dynamics on a fusion data set, and each of these refer to state variables in plasma dynamics. And you can just look at the x-axis, what that measures calibration error. And you can see that using this loss function tends to reduce or produce conditional quantiles that have low calibration error. Okay, so thus far we looked at univariate models where the targets are single dimensional. And we're looking at methods to optimize for calibration during training. And that sort of falls under the methods called pre-hoc. So you're trying to optimize during training. And we're going to move on to multivariate settings where the targets can be multidimensional. And specifically, we're going to now be looking at post-hoc methods. So we're not going to be optimizing for calibration during training of the predictive model, but we're going to look at the setting where given a pre-trained model, you want to apply maybe some perturbations or learn a simple function that allows you to derive.
CH.
Yes.
Oh, really?
Yeah.
Doomsday button on this thing.
Thanks. Okay. Yeah, so again, we're gonna be looking at multivariate settings where the targets are now multidimensional, and we're gonna be looking at post hoc methods, which just take in a pre-trained model, then hopefully modify it, perturb it in a way that's more calibrated than it originally was. And the motivations for trying to move to multi-dimensions is that many problems in the real world are actually multidimensional. So suppose you have a weather prediction system. You might have a model that doesn't just predict cloud cover, but maybe cloud cover plus rainfall. Other examples include you have a drone and you're inputting actuators in a simulator, and you want to predict the XYZ position of this drone given the actuator settings. Or maybe in materials, you have a concrete recipe and you want to predict both the compressive strength and the tensile strength of the resulting concrete. And obviously this becomes, being able to model multi-dimensions becomes much more important when there actually exists correlations between each of these output states or variables. And it turns out that calibration in multi-dimensions is actually highly non-trivial. Recall that in the previous section when we were looking at univariate settings, calibration was defined in terms of quantiles, but in multi-dimensions, quantiles are not well defined. And so we can't really work with quantiles anymore. And in lieu of working with quantiles, you may work simply just evaluate calibration for each output dimension separately. So you're just looking at the marginal distribution of dim 1 and dim 2 separately. And that obviously has pitfalls, especially when there exists correlation in the target and predicted distributions. So if you just look at calibration of each of the dimensions separately, you're perfectly calibrated, but it's pretty clear that your predicted distribution has the complete opposite correlation as the ground truth distribution. Yeah, so here's what we propose to do. So you cannot work with quantiles anymore. And quantiles, again, are just a method to describe your predicted distributions. And another way to describe your distributions are actually through samples. So we propose to work with samples instead. So instead of specifying the conditional quantiles to describe a certain distribution, we're just going to be producing a set of samples. And that will be used to not only make your predicted distributions, but also to sort of glean into the ground truth distributions as well. And once you're working with samples, one way that you can simplify the problem of calibrating in multi-dimensions is to actually just use projection functions that map to a scalar. So suppose you had a projection function g, which maps to variables z, which are reals, so they're scalars. And you can transform this two-dimensional samples in the target space into these one-dimensional scalars. And with one dimensions, we already know how to assess calibration, recalibrate. So you can work with quantiles again in single dimensions with the projections. So all of these are in Z space. They're all scalars. We started on Y, and now these are Z's. And it turns out that if you, we conjecture that you can actually use any projection function for G, but if you use the predictive PDF, so f hat of Y given X, then the projections correspond to demarcating the regions that are called highest density regions, which is a notion that's sort of well studied in statistics. And in a nutshell, HDRs, or highest density regions, are prediction sets or regions which have the highest predictive density. And in single dimensions, we can take a look, we can see an example that sort of illustrates what they are. Suppose you wanted to make a prediction interval with a probability P. Previously, we were looking at quantiles, so we were looking at which value Y, below which we can iterate to get probability P. But now we'll be looking at the value of the function itself, f hat, and looking at which value of f hat above which value of f hat is basically the lowest value of f hat, for which the regions that have higher density have probability P. I hope that makes sense. So both of these, yes, this region has probability P, that region has probability P, but they're basically two different ways of constructing prediction sets for regions. And in multi-dimensions, you can think of the same. So you can think of them as level sets of same colors. Okay, so given the notion of HDRs, and now given these projections, Z's denote the HDRs, the boundaries of the HDRs. We can define a notion of calibration using HDRs and say, if Y is in the PHDR prediction region, P% of the time, then you can say that you're calibrated, HDR calibrated. And here's an equivalent way to write that equation using variables, the projection variables. And using this notion of HDR calibration, we can see that it reveals the miscalibration of the predictive distribution. So whereas each of the marginal calibration reliability diagrams did not display any miscalibration, if you measure HDR calibration, there is you can see that there is miscalibration. And thus far, we've shown a way that you can assess calibration for multidimensional predictions. Suppose we wanted to recalibrate these distributions. So this is known as post hoc calibration. You already have a predicted distribution, and you're going to modify it slightly and make it more calibrated. And it turns out that this mapping, the reliability diagram, which we can denote with the function R, which maps from scalars to scalars, or probability values to probability values. This mapping in composition with the predictive distribution of the projections is HDR calibrated, because this basically tells you how much you are off from being calibrated. So you can apply this mapping to your predicted distributions in the projected space to define a new distribution that is calibrated with respect to the notion of HDR calibration. And how we can actually do this, so how do we actually express this is again with samples. And it's actually pretty simple. So we're working in Z space. And suppose we're looking at this bin. So this is between two HDRs. And we have a lot of density with respect to the predictive distribution. And there's low density with respect to the ground truth distribution. So we can say in this bin, we need to undersample. And what we can do is from our predictive distribution, we sample a bunch of points. And then again, we're working with projections with the predictive PDF. We apply the PDF on each of these samples to get the projection Z. And again, Y is multidimensional and Z is univariate, it's single dimensional. So these are scalars. And then we have this composition distribution, which tells us how much we should resample by. So from this set of Z samples, we can resample according to this new density. So here's a subset because we needed to undersample. But recall that, we're working, in the end, we still want to get samples in Y because that's the target variable we care about. We don't really care about Z. These were just projections. So to translate these back into Y, all we have to do is keep track of which values of Y corresponded to each of these projections. So we had like Y, Z2, Z5. All we have to do is collect Y2, Y5, etc. And once we collect these resampled set of samples from Y, we can say that these samples are now then HDR calibrated. And these are samples in the target space that we care about.
Can I ask a question?
Yeah.
How do you make sure that the projection is invertible?
It doesn't have to be. See, yeah, if so, if you didn't want to keep track of which Y's corresponding to each Z, then you need an invertible projection such that from Z, you can go back to Y. But as long as you keep track of which Z's you're collecting and the Y's that correspond to each Z, then you can, basically you have a separate set that's resampled, that's Y's, that each have a one-to-one mapping to each of the Z's that you're working with. Yeah, so all you need to do is keep track of which Y's correspond to each of the Z's. But it's a good point. If you don't keep track of it, you need an invertible projection. Yeah. Okay, so here's a visualization of what that sort of looks like, and it's actually very simple, despite all the hairy equations. Suppose you had a ground truth distribution in blue. It's a very thin, sort of tilted Gaussian, and suppose your predicted distribution was this isotropic Gaussian, which is often the mean, also often the correlation, and it's a two-dimensional target space. So when you're looking at HDRs, what you're doing is you're drawing contours or the level sets of the predicted density, which each correspond to each of these rings. So each of these rings correspond to an HDR. This would be the smallest HDR because you would expect the least amount of density here, whereas the widest the ring would be like the 100% HDR. You would expect all the data points to fall, inside this ring, or nearly all of the data points. And the initial prediction, this prediction has horrible calibration according to HDR calibration. And before we go on to resampling, one thing you'll notice is we've proposed to resample from each of these HDRs, but then one caveat of that is that you're stuck with the shape. So if you had isotropic predictions, then your recalibrated distributions will also be isotropic. And that seems like a detriment, right? So we propose a phase before resampling, which we call sort of the adjustment phase. So based on maybe a held out data set, you can first adjust for the location of the predictive distribution such that the means are roughly equal. And then you can also adjust the correlation in the output dimensions, and that adjusts for the shape of the predictive distribution. And it's hard to tell a little bit, but all of the ground truth data points are actually concentrated in the inner rings of this new sort of adjusted predictive distribution. And if we measure HDR calibration for this predictive distribution, it sort of reflects that. So once you have this adjusted HDR, you can resample from each of these level sets according to the densities provided by the recalibration mapping, this one. And if you measure after the resample procedure, the second phase, which is resampling from each of the HDRs, you achieve good calibration according to the HDR calibration metric. So in conclusion, we first looked at univariate calibration and pre-hoc methods to basically train for conditional quantiles, which achieve calibration in single dimensions, and then extended it to multi-dimensions. Introduced a notion called HDR calibration, which allows you to assess calibration in multi-dimensions and also recalibrate your predicted distributions in multi-dimensions such that the output is more calibrated according to the notion of HDR calibration. And I want to sort of conclude with something called the Uncertainty Toolbox, which is an open source software that myself and some collaborators here at CMU and elsewhere also contributed to. If you're interested in predictive UQ, I think this will be a pretty helpful, useful tool to you. It's got a lot of the algorithms that we discussed. There we are implemented in this repo, and it's turned out to be fairly popular in the uncertainty community as well. And that concludes my presentation. Thanks for listening and happy to take any questions. Yeah.
In your first part, when you were adjusting the, calibration interval
Yes.
by updating,
Yes.
are there any guarantees of conversions there or, when?
There are no guarantees of convergence, but I think the hope is that if you work with large enough mini batches, then they provide a close enough approximation of the level of calibration that your model currently achieves. But yeah, there are no formal guarantees that it converges. I think in the limit of the mini batch, then it absolutely should, because you're basically looking at the whole data set.
But like it could get worse also.
Yeah, it could get worse. Yeah, I guess if you look at the training plots. Yeah, it can get a little worse. Yeah.
The one,
Yeah.
the second part, with what you're calling HDR are actually not specified by levels, right? They're just some minimum volume sets with high, like you specify a mass, probability mass, and they're minimum volume sets, but.
Yeah, they're minimum. Yeah, you specify a mass and then there are regions that contain that mass.
Right.
Yeah, but you can also view them. So you have your predicted PDF. If you apply the predicted PDF to the samples from this predicted distribution, then you can draw, I guess, a density plot of those projected samples. And then here, they correspond to the quantiles. So each quantile specifies in the projected space what the, I guess, threshold should be for the PDF value for each of the HDRs. Yes.
I wonder whether there's some theoretical result about if I know the marginal quantifier of different attributes, and I know the correlation between them, and is there some correlation between the marginal quantile and the HDR?
Marginal quantiles and the HDRs. So you're saying if you know the marginal quantiles of each of the dimensions?
Yeah, and I know the correlation of the of the different dimensions.
And you're asking, does that give you maybe a closed form solution for what the?
Yeah.
I suspect there could be if you have simple parameterized solution distributions like Gaussians. But if it's highly multimodal and complex, maybe not, because that's not enough to fully characterize the distribution. But yeah, I suspect that for simple distributions, there should be a way to actually just recover the ground truth.
Thank you.
Yeah. Yes.
Yeah, so for your first part of the presentation, you mentioned that your algorithm calibrates for every quantile. Is that correct?
Yeah.
So would that mean that the final outcome of this algorithm would be the similar to estimating for the conditional probability function?
It would be. So the output of the learning would be a function which takes in both x as the input and a p, which corresponds to the quantile, and it outputs the conditional quantile corresponding to that p at the x, the input point. Yeah, in a way, you're describing the conditional distribution with quantiles.
Yeah, so I was thinking, how would you argue in computation aspect, how would your algorithm be different with an algorithm that just directly estimates for the conditional density?
I see. What kind of methods are you thinking about when you say directly estimate conditional densities? Just non-parametric.
I know there are KDE methods for Narada-Watson estimators for that. So yeah, I was wondering how would you compare these two?
So when you use those estimators, I think you're not recovering functions, right? You're actually just recovering like a single value for as the approximation of the quantile. Is that correct? Oh, I see. Oh, no,
Well,
you're,
They are like non-parametric.
Oh, I
estimators.
see, I
They
see.
do.
mm, I think it's hard to compare, like. I think each time you want to produce an estimate with those estimators, it incurs some computation, some fixed computation, right? I guess like
Right.
according to some kernel, or like distance measures. This is a iterative learning algorithm. And once you finish training, then you can just use it for any like in distribution data point. So I think it's a little hard to compare.
Yeah, I see.
Yeah.